So far this week, you've learned how to develop an equivalent circuit model of lithium-ion battery cells step by step. We started very simply with a constant voltage source, and we enhanced the model by adding a state of charge dependence to this voltage source, and then we enhanced it again by adding an equivalent series resistance term, and then we enhanced it again by adding a resistor-capacitor pair, and showed that if we add enough of these resistor-capacitor pairs, we can approach an electrochemical model of a battery cell. So the process that we've been taking has been to modify slightly the previous model by adding components in order to better and better represent the dynamics of a physical battery cell. And so the resulting model that we have so far is pretty good. But it still doesn't describe everything that we see in a lithium-ion battery cell. In particular, it turns out that if we let the battery cell rest long enough, the diffusion of voltages does decay to zero, and so the model's voltage prediction decays exactly to open circuit voltage over time. But in a physical battery cell, we find that's not the case. Instead, we find that for every state of charge, there's a range of possible stable final voltages and not a single stable final voltage equal to the open circuit voltage. To illustrate this, I show you a picture of data collected in a laboratory test here at the University of Colorado, Colorado Springs. And let me describe what's happening. Notice that this is plotted versus state of charge, and it's not plotted versus time. We're starting the test actually at the top right corner with this cell fully charged, and then we slowly discharge this cell, so the voltage is going down at the same time that state of charge is going down, until we hit the minimum voltage at the minimum state of charge of 2.5 volts at 0%. And then we very slowly charge this cell up to 95% of its capacity, and then we discharge down to 5%, and we charge up to 90, and we discharge down to 10, and so forth, to make these concentric loops that are getting smaller and smaller over time. Now, the rate of charging and discharging was very slow. We used a value of current, which was the C/30 rate, or in other words, it would take about 30 hours to completely discharge the cell or to completely charge the cell at this rate. And the reason that this very slow rate was chosen was such that the cell would be essentially in equilibrium at every point in this test. And so it's not completely true, but it's at least close to true, that every data point that you see plotted is a steady state or a rest voltage of a battery cell. So we didn't find an exact open circuit relationship. In fact, we see that there's a range of values for this open circuit relationship. In this case, in the mid-SOC region, between about 3.25 and 3.35 volts, about 100 millivolts difference, which is quite a bit. If we ignore the existence of this phenomena, it's going to lead to very large state of charge prediction errors when we look at how to compute state of charge in the third course in the specialization. For example, suppose that you measured in a real battery cell a voltage of 3.3 volts. Well, according to this, 3.3 volts could correspond to any state of charge in the battery cell, even at rest, between about 10% state of charge and about 90 or 95% even state of charge. Which means if we measure 3.3 volts and we don't have a model of this phenomena that we're showing here, it could be almost any state of charge. And voltage do not tell us very much information about what the state of charge actually happens to be. So this phenomena that we're looking at is known as hysteresis. And the hysteresis says that there's going to be a different steady state value of the rest voltage depending on if I've recently been charging or discharging. And so not only the value of current is important, but the history of that value is important as well. And hysteresis is quite different from diffusion voltages in one very important way. And notice this, be very careful to notice this. The diffusion voltages would always cause the cell voltage to decay to some constant value over time. if the cell is allowed to rest. And so diffusion voltages change simply as a function of time, if you will. But the hysteresis voltage does not change at all if the cell is allowed to rest. A hysteresis voltage changes only when state of charge changes. And you can see that in this plot because the bottom axis of the plot is state of charge. It's not time. So the direct change in hysteresis is due to a change in state of charge, not due to any direct change in time. So two very different phenomena, which is why we need different equations to describe how these two different phenomena work. Okay. Let's try to isolate the hysteresis component itself so we have a better idea what it looks like. So I took that plot from the previous page and I subtracted from it the open circuit voltage value at every point in time. And the method for finding that we'll talk about next week, but it's roughly equal to the method that we looked at in the previous lesson. So we subtract the open circuit voltage relationship from that cell, and what's left over then is essentially the hysteresis voltage of the cell for that entire previous test. And we look at this and we try to think about how would I make a model to describe this, so some hopefully simple model. So we can say, well, it looks like there could be a maximum positive and negative value of hysteresis at any state of charge. So we will call that M. M as a function of state of charge is the maximum value, and here we are assuming that the maximum value, at least for now, is uniform whether I'm charging or discharging. The value of hysteresis, though, is different whether I'm charging or discharging. So if I have been charging recently, I have a positive value of hysteresis, and if I've been discharging recently, I've got a negative value of hysteresis. So this envelope of the hysteresis that we see here doesn't depend only on state of charge, but it also depends on whether I'm charging or discharging. And we can think of that as either the sign of the input current, would tell me if I'm charging or discharging, but also the sign of Z dot tells me if I'm charging or discharging. So we now slightly modify this M of Z to be M of Z and Z dot to include that effect. The hysteresis also changes in a way that sort of looks like a resistor-capacitor decay, but remember that it decays towards its maximum values when SOC changes and not when time changes, but there are some similarities. So whenever current changes, so if I go from discharge to charge, my hysteresis is going to go up and then decay towards the maximum value. Or when I go from charging to discharging, the hysteresis value goes down and then decays toward the minimum value. So this kind of suggests that hysteresis can be modeled as a differential equation in the rate of change of state of charge. We take all of these observations and think of, well, what might a model look like that would capture all of these ideas? So here's a model that we propose. It says that the amount that hysteresis changes for every amount that state of charge changes, so this is not H dot, notice, this is not the change in hysteresis versus time, but it's the change in hysteresis when state of charge changes. We're setting that equal to a gamma parameter value times the sign of Z dot, so which way I'm going, am I charging or discharging, times M minus H, where H is the actual amount of hysteresis. So let's think about this. The maximum value of hysteresis, M of Z and Z dot, is positive for charge, so when Z dot is bigger than 0, and it's negative for discharge in order to match the experimental results that you've seen already. The M minus H term on the right side of this equation causes the hysteresis rate of change to be proportional to the distance that hysteresis happens to be away from the major hysteresis loop. So if this difference is large, M minus H is large, I'm a long way away from the maximum value of hysteresis at this point, which means that the dH by dZ is going to be large in magnitude, so I'll move more quickly. But if h is almost exactly equal to m, then m minus h is very small, and so the rate of change of hysteresis versus a change in state of charge is going to be small. So that term there is helping us to get this kind of an exponential shape of decay of hysteresis towards either the maximum charge or maximum discharge curve. The positive scalar gamma in this equation tunes the rate of change. So if gamma is large, then hysteresis changes relatively quickly. If gamma is small, it changes relatively slowly. So it's like a time constant, but it doesn't operate in time again. It operates as state of charge changes for this cell. And finally, the sine of z term is included there to make sure that the equation is always stable no matter whether we're charging or discharging, so it doesn't just go crazy. So the figure that you see on the slide shows again in blue the sample result that we had earlier from the lab test data directly. And here I've spent a little bit of time, not too much time honestly, fitting the red curve, which is a model of hysteresis, to this equation. And I chose for this to have a gamma value of 0.06 and kind of putting all of that in there. No, sorry, gamma was 50, sorry. And that m was 0.06 times the sine of z dot. So you can see that the red curve sort of approximates the blue curve. It's not perfect, but it at least gives you some of the major features of hysteresis that we see in the lab test data. So it's not a great model, but it's better than no model at all. Now, the equation that we've developed so far is a differential equation in state of charge, not in time, and so it doesn't really fit well with the model that we have developed in earlier lessons where everything is a derivative with respect to time. And we really would like to be able to change the hysteresis equation into a form that is differential in time instead. And we can accomplish this by taking both sides of the hysteresis equation that you saw in the previous slide and multiplying both sides by dz divided by dt. And when we do that on the left-hand side, the dz's cancel, and so the left-hand side becomes dh by dt, which is h dot, which is of the form that we desire. So that is fantastic, perfect. Now on the right-hand side, we're going to think of dz by dt in a little different way. So on the right-hand side, we'll notice that we have a sine of z dot times z dot. And if you go through the mental exercise to think about what that looks like, x times sine of x is actually equal to the absolute value of x. And so those two terms combine to be the absolute value of z dot. And then we go to the state of charge equation in continuous time and we evaluate what is z dot. Oh, we know what z dot is. Z dot is equal to negative eta times I divided by q. So when we do that, we can rewrite the first equation on this slide as the second equation on the slide. Left-hand side becomes h dot. The first term is going to be the gamma times sine z dot times negative h times dz by dt, and that becomes negative absolute value of eta I gamma over q times h. And then the final term is the gamma times sine z dot times m. And again, times dz by dt, and the z dot sine z dot gives you the absolute value of z dot, so I've got eta I times gamma all over q, absolute value, all times m. And I could bring the gamma inside of the absolute value because we said on the earlier slide that gamma was always positive. And so we have now an equation for a continuous time model of hysteresis. We need to convert this into discrete time, but the good news is that we can use the result from earlier this week for converting a first-order differential equation from continuous time to discrete time in order to do that. And I don't go through all of the steps here, but you can do that on the side and verify that this result is accurate, that we have the discrete time equation that next hysteresis is equal to e to the negative eta I gamma delta t over q times h, then plus 1 minus e to the negative absolute eta I gamma delta t over q, all times m of z and z dot. And this is our discrete time hysteresis model. Notice that this is a linear time-varying system. The values on the right-hand side that multiply h and that multiply m are both functions of the input current at any point in time, and so these values will not be constant but will change with time. But that's okay, we can deal with that. We also have to wonder, what do we use for m, this maximum hysteresis? And the simplest form, which I used in the previous example, is to set m of z and z dot equal to a number m times the sine of the input current. And we don't have to do that, but that's the way that I'm going to assume pretty much from now on. And when we do that, we can rewrite the first hysteresis equation on this slide as this second one, where I have expanded out the function m as negative constant m times sine of input current. When we use this particular representation, it turns out that the hysteresis value is always between plus and minus the constant value of m. And this hysteresis variable h has units of volts. And so you can think of m and volts as the magnitude of hysteresis. So that's a good way to think about it. Now, the equation on the previous slide was perfectly fine. But it turns out when we get into the task in 2 weeks of trying to optimize the values of the model based on lab test data, that the form of that equation was not as useful as it could be. On this slide, we slightly changed the form in ways that don't appear to be any different, but it allows us to use some simpler methods to find the parameter values of any particular cell model based on lab test data. So what I've done is I've taken that previous equation and I've divided the input by m, the constant value, and then on the output I say that the hysteresis voltage VH is m times h. So this hysteresis state, which used to be measured in volts and used to go from plus m volts down to minus m volts, now is unitless. So in this equation now h goes between -1 and 1 always. And in order to convert that to a voltage, I have to multiply the hysteresis state by m to give me VH in volts. So it looks a little bit more complicated. It's not a lot more complicated, but it turns out it's going to make life much easier later on. So all we've done, again, is we've moved m from the input side of the equation into the output side of the equation. The type of hysteresis that you've seen so far this lesson is what I call dynamic hysteresis. It's hysteresis that changes its value. It evolves its value over time, if you will, but as state of charge changes. It's nothing that happens instantly. If you go back and you look at the actual data, it does appear that the data has an instantaneous part as well as a dynamic part. And so we can think of modifying the model one more time to add an instantaneous hysteresis component that changes immediately when the sign of input current changes. What we're going to do is we're going to define a new variable, which is S of k. S of k is the sign of the input current, S for sine. And so under most conditions, we'll say S of k is just equal to the sign of input current, which means that it's 1 if the current is positive and it's -1 if the current is negative and it's 0 otherwise. But we know that when state of charge is not changing, that the hysteresis value is also not changing. And so really we don't want to keep track of the instantaneous sign of input current so much as we need a way of knowing when I've moved from charging to discharging. So when has the direction of input current changed, and the resting state is not going to change the direction of current. So if I go from discharge to rest back to discharge, the sign of input current should be consistent throughout all of that. But if I go from discharge to rest to charge, then it should switch from one sign to the other when I hit the charge step. And so this sine function, the S of k, maintains a memory of whether I've been discharging or charging more most recently. And so S of k is always either +1 or -1. It's never 0. And so if the SGN function would tend to make S 0. We don't allow that. We just keep the previous result. So then, with that definition of S of k, the instantaneous hysteresis is modeled as H sub I for instantaneous, is equal to m0 times S, where m0 is a different number from m. It's the instantaneous hysteresis magnitude as opposed to the dynamic hysteresis magnitude. And therefore the overall hysteresis VH, which is the hysteresis voltage, is m0 times S, the instantaneous part, plus m times H, the dynamic part. And here we see the same data as before with the combination of the instantaneous and the dynamic hysteresis models. And you can see that, again, it's not a perfect model, but it is probably better because the vertical blue lines have now been modeled pretty well by vertical red lines, and this allows us to adjust the time constants of the dynamic model to capture those parts a little bit better also. To summarize what you've learned about in this lesson, you've learned that hysteresis is a path-dependent voltage that does not decay to zero as the cell rests. This is different from diffusion voltages, which do decay to zero when the cell rests. The lab evidence indicates the presence of both an instantaneous type of hysteresis and a dynamic type of hysteresis. And in this lesson, you've learned about a simple model of hysteresis that's honestly not fantastic, but it's better than no model at all, even if we use constant parameter values for gamma and for m0. There are much more advanced hysteresis models that researchers are looking at, and indeed our research team is also looking at some of those as well, but this model will be sufficient for our purposes for this specialization. It is possible to improve the modeling of hysteresis even with this simple model if we use state of charge dependent values for m and m0 and so forth. And that can actually get you pretty far towards modeling hysteresis very well. So at this point, we've now described all of the elements of the type of equivalent circuit model that we use throughout the rest of the specialization. There's one more lesson this week before a summary, and that lesson is really going to bring everything together in one place so that you've got a really good permanent reference to go back to when we're talking about circuit models, and you can refer to all of the equations at one location. So one lesson to bring everything together, and then a summary lesson will wrap us up for this week.